Considering the a great many developments that radiance at us in the atmosphere, it is difficult to accept. But there is a lot to propose that the smooth way is in an especially unfilled locale of room. And as a matter of fact, our situation in a massive void could indeed even end up being a genuine stroke of karma. After all, it makes it easy to break the secret of the alleged Hubble pressure and finally make sense of why the universe is extending quicker in actuality than it ought to. Hypothetically, anyway, this astonishing suspicion has one little impediment. Stringently speaking, there ought to be no such uncovered spots in space at all. And to make sense of the inconceivable void, we need to forsake the laid-out thoughts of Einstein and company. There is no resilience allowance here, one or the other. While the hypothetically resolved development speed of the universe is assessed at around 67 kilometers per second per megaparsec, actually, the universe presents itself as a real heavy foot and is in any event extending at a speed of 73 kilometers per second per megaparsec. Since these qualities appear to be very conceptual at first glance, we should first explain what they really mean and how outrageous the deviations between the anticipated and noticed extension rates truly are. In standard terms, the speed at which the universe is presently extending is communicated as the supposed Hubble constant. And it's no incident that the word Hubble is essential for the name. After all, the American Edwin Hubble was quite possibly the earliest space expert in the late 1920s to understand that different worlds in space are creating some distance from us, or, in other words, that the universe is continually growing. Anyway, the universe isn't venturing into a current space. No, rather, space itself is continually developing. In regards to the unit of the Hubble constant, which has all the earmarks of being everything but natural as kilometers per second per megaparsec, it should be noted that a megaparsec corresponds to about 3.26 million light-years, while a light-year is around 9.46 trillion kilometers. Moved to the hypothetical Hubble constant, this amounts to just that the speed at which the systems in space get away from one another increments by 67 kilometers per second each 3.26 million light-years. Changed over, the universe hence extends at a speed of 244,000 kilometers per second per megaparsec. But as already referenced, this only applies on paper, since when we decide the worth of the Hubble constant in the course of direct perceptions of supernovae, gravitational focal points, variable stars, or on the other hand, red giants, it unexpectedly sums to 73 kilometers per second per megaparsec, or 264,000 kilometers per hour per megaparsec. So we are managing here with a deviation of something like 20,000 kilometers per hour for every megaparsec, which is something like quite possibly one of the greatest research riddles within recent memory and is altogether referred to as the Hubble strain. How the James Webb Telescope confirmed the Hubble strain is a crucial question. But how can this even be? How might it be that a significant foundation of the standard cosmological model gives us such an enormous riddle? Well, the easiest solution would be that past perceptions were dependent upon essential estimation mistakes that mutilated the genuine worth of the Hubble constant. And to test exactly this suspicion, the group led by Nobel Prize winner in physics, Adam Rees of Johns Hopkins University in Baltimore, has broadly assessed the data gathered by the James Webb Telescope over the last 2 years and contrasted it with that of its logical ancestors exhaustively. The specialists analyzed the distances of 16 supernovae, as well as red giants, variable stars, and an exceptional class of carbon-rich giant stars. Yet the baseline of the assessment of the most broad Webb informational collection to date was a sobering outcome. The Hubble strain was simply affirmed. Indeed, more unequivocally, the summarized outcome yielded a development speed of 72.6 kilometers per second per megaparsec, which, to put it lightly, raises doubt about the possibility that the deviations from the standard model are because of estimation vulnerabilities or blunders from past space telescopes. Be that as it may, how did the analysts arrange their results? Well, it was very straightforward. Adam Rees honestly conceded that our comprehension of the universe could basically be inadequate. Appropriately, it's possible that we have, up until this point, neglected something vital in our cosmic sensible standard model, for example, a new part that has given the universe a surprising motivation after its creation. But at the same time, it's conceivable that the foreboding dark energy proposed as the main thrust behind the accelerated expansion of the universe has changed. Anyway, obscure, fascinating particles, changing electron masses, or certain attractive fields are consistently counseled to give a clarification for the Hubble strain. But in this plenty of arrangements, the way to progress could be hiding in the void of space. The incomprehensible void, as an answer with a width of 100,000 light-years and an expected 100 billion stars, is probably not what you would call a vast no-man's land. Despite this, our home galaxy and its neighborhood could be situated in the center of a colossal void that is in a especially vacant or matter-uncharged region of space. However, what is the foundation to this presumption, and for what reason might it at some point lead to the solution of the enticing Hubble strain? To understand this, we first have to imagine the overall design of the universe. After all, stars and planets don't travel through space alone. They are known to organize themselves into systems, which in turn come together in galaxy clusters that form superclusters. For quite a while, analysts have believed that these superclusters represent the largest lucid designs in space. Anyway, large-scale studies have since uncovered that the superclusters are by no means distributed like cabbage and turnips in space but are themselves also part of a larger organization-like construction. The lattices of these superclusters form the purported fibers, long filaments that, here and there, range a few million light-years simultaneously. The cross-sections of the large organization also lengthen across huge, basically matter-free air pockets. And that's precisely the pivotal point. Truth be told, knowing where matter density wins is fundamental for determining the astronomical expansion rate. In light of this, only along these lines might we accurately interpret the corresponding measurement results. Exhaustively, the research group, led by Ben Hite from the University of Wisconsin-Madison, identified signs a couple of years back that there is a relative void around the Milky Way and its environment. To this end, the investigation of spectroscopic surveys of space had uncovered that we might be in a void that extends over 1 billion light-years, which in turn is multiple times bigger than would be common for such void regions generally. And furthermore, just a few months ago, specialists from the universities of Bonn and St. Andrews mentioned similar observable facts, which once again gave the void hypothesis new force. To outline this, the specialists analyzed our position in space with an air pocket in a cake. Around the air pocket, the density of matter is thus higher. On the other hand, this also means that gravitational forces exude from this surrounding matter, pulling the galaxies in the center of the air pocket towards the edge of the pit, making them eventually get away from us faster than would actually be expected. The mysterious deviations of the Hubble constant, which have been keeping analysts on their toes for so many years, could thus be explained simply by such a neighborhood underdensity. Indeed, one more group of space experts recently assessed the average speed of a huge number of galaxies found 600 million light-years from us and found that the far-off star systems are moving away from us multiple times faster than the standard model of cosmology permits. And for an explanation that is as simple as it may be significant, according to our laid-out theories, such underdense districts should not really exist at all. Goodbye to Einstein and company. The reality that such grandiose voids are inconceivable on paper is because of the fact that matter should be evenly distributed in space on large scales, and not separated into conglomerations and void bubbles. But as per the study creators, we shouldn't forget one thing. Our standard model depends on a theory of the nature of gravity proposed by Albert Einstein. But what if the creator of the theory of relativity was wrong? In other words, what if the gravitational forces really act in an unexpected way from what Einstein had expected at the time? Well, then we would have arrived at the adjusted theory of gravity that the working groups from Bonn and St. Andrews utilized in their virtual experiences to be more exact. We are dealing with the so-called modified Newtonian dynamics, or M, which was proposed as early as 1983 by the Israeli physicist Mordechai Milgram as an alternative to dark energy. M describes another option theory of gravity in which the rotational behavior of galaxies is explained by adjustments for the conditions of movement of matter in the gravitational field, and which survives totally without the impact of dark energy. And although the speculation is still controversial and has not advanced past the status of an outsider theory, It makes predictions that agree with real observations in space. Besides, M also predicts the presence of massive void air pockets in space. As mentioned, the problem of the Hubble tension would immediately disappear if, in fact, gravity acts as Milgrom believes. This would mean that there is just a single constant for the development of the universe, and the noticed errors would only be attributed to anomalies in the distribution of matter. However, at the same moment, this would also imply that we would have to leave some major assumptions of Newton's law of gravity and Einstein's general theory of relativity, and it is not yet clear how much this outsider theory will stand its ground in the field of established models. We guarantee that only one quick snap is all it takes to never miss another video from us again. Feel free to hit the thumbs up button and subscribe now to stay up to date. From this point forward, we'll see you soon.